How to improve the TPS performance of Filecoin to 64,000 or even 64 million. At present, Filecoin is most likely the first blockchain project to support realistic applications. However, the main downside of Filecoin is low transaction throughput. That is, low transactions per second, or TPS. For now, sharding technology is the most promising solution to improve TPS performance. And the proof of spacetime, or post mechanism in Filecoin, is currently the only way to achieve the security in sharding. Therefore, we combine Filecoin and multi-layer sharding technology to propose a new high-performance blockchain with high sharding security. 1. High performance. Achieve 64,000 TPS at 1,024 shards, and has the capacity to achieve 64 million TPS at 1 million shards. 2. Low bandwidth occupancy. It can run on a 30 megabits per second to 50 megabits per second ordinary home network, and the protocol occupies no more than 5 megabits per second of bandwidth. 3. High security. It has a sharding security capability of up to 10 to the negative 8th power. In order to achieve this high-performance blockchain, many engineering and technical problems need to be solved. First of all, the communication needs to be sharded. All blockchain projects now rely on the global network broadcasting, meaning that all nodes need to sync all transactions and block information about irrelevant shards, which is extremely inefficient for network bandwidth. We have implemented a trusted routing scheme on the P2P layer to enable transactions to be transmitted only in the corresponding shards and between the related nodes, reducing the communication volume of nodes to 1/n of the original. The storage also needs to be sharded so that each node just needs to store the relevant data. We have added an active data spreading mechanism to IPFS, increasing delay performance of data retrieving. It makes all storage nodes form a CID-based, on-demand access, high-efficient P2P storage system. Data can be stored via one node and read through any node, which can minimize on-chain data broadcasting and avoid the data synchronization of nodes when it expands the sharding elasticity. Even if the communication is sharded, in order to ensure the data consistency, the cross-shard transaction data, or their merged hash results, must be transmitted on-chain. It can be proven that the correlation between the bandwidth required for the cross-shard transaction and TPS is expressed by O TPS to the power of 2 over L-1. Therefore, in a common root shard two-layer network, the correlation is O TPS to the second power, O TPS to the first power in a three-layer network, and O TPS to the power of half in a five-layer network. The P2P storage network is needed to achieve the optimized communication after network sharding. The sender shard stores the shard transaction data into a P2P storage network, and the corresponding hash or CID is written to the chain. After receiving the hash or data CID from the chain, the receiver shard reads the corresponding data from the P2P storage network. P2P storage enables the data to be transmitted only in relevant shards, that is, only transmitted in necessary nodes. In any sharding network, each shard only has a fractional proof power of the entire network, and an attacker can concentrate all his proof power to a particular shard to take advantage of the dispersed computing power. For the space-time proof algorithm in Filecoin, if the data chain matching is implemented, the proof power must gradually increase from 0 in a certain shard, and the proof power is obtained by on-chain matching. It is the only schema that can guarantee the security of the sharding system, and it will be the cornerstone of the security of the sharding system. After sharding, the rollback avalanche problem must be resolved. That is, the rollback of any one of the shards in the sharding system will result in the rollback of the associated other shards, while the rollback of the related shards will further result in the rollback of more shards. The solution to the rollback problem is to process only the blocks that have been finalized in cross-shard transactions, which results in more delay time in the confirmation of cross-shard transactions. We have developed a universal consensus algorithm based on dynamic election and proxy voting to achieve the finalization within a block time, which resolves the rollback avalanches and optimizes the delay time in cross-shard transactions. A blockchain that meets actual applications must have smart contract functionality. The solution that can only execute contracts on one shard cannot meet the performance requirements required by actual applications, and the contracts that can be executed on multiple shards will generate cross-shard data access and the need for data synchronization. By splitting the data into in-shard and cross-shard data, and designing the reading and writing processes of cross-shard data as a specific transaction primitive, we can realize the multi-shard execution of smart contracts by using the existing way to access this shard data and increasing the access of specific transaction primitive to cross-shard data. We can realize a high-efficiency and low-cost multi-shard execution scheme of smart contract. The above scheme solves the problems of communication and storage between shards. In addition, it is necessary to implement an in-shard consensus algorithm to meet the requirements of sharding. The consensus algorithms that meet the requirements of sharding also need to satisfy with the following 6 requirements. 1. Random block proposer. 2. Fair incentive system. 3. Fast finalization ability. 4. Maintain active in an asynchronous network. 5. The requirement of low communication bandwidth. 6. High sharding security. We have designed a universal consensus algorithm based on dynamic agent election. The key logic is divided into 2 processes. Each 1,000 blocks is called an era. Before each era starts, the committee election is conducted first, and a certain number of committee members are elected. When each block is produced, it goes through several processes as follows. 1. Each candidate node's CI calculates its own block proposal probability by OP equals variable random function over 2 to the 256 power times PI over PAll. 2. Candidate node CI shows its OP to committee member DI. 3. After a certain period of time, the committee member DI sorts all the received OPs and obtains the votes by a function VI is equal to F, C1, C2, and Cn, and sends the votes VI back to the candidate nodes C1, C2, and Cn. 4. The node records the received multiple votes V1, V2, calculates the weight W of the votes obtained by itself, adds the weight proof to the blocks, and then broadcasts the votes to the relative shard. 5. Other nodes in relative shards select the blocks in basis of the received weight of the block. Obviously, the blocks with more than 51% weight are always finalized. It can solve the aforementioned problem of rollback avalanche. After completing the above-mentioned in-shard consensus and cross-shard communication and storage, Filecoin will have the capacity of bringing billions of computers together, achieving 64 million TPS throughput, thousands of zettabyte of storage capacities, and could replace the existing CDN storage services. Moreover, when the trusted routing is combined with flexible storage distribution and P2P traffic accounting capabilities, it can meet the requirements of streaming media applications, such as on-demand video and live broadcast, enabling Filecoin to store the core facilities of streaming media distribution and further improve the value of Filecoin.